Thank you very much. Thanks for inviting me to come and talk to you. I've actually got quite a jam-packed presentation, but I can sort of tailor it round a little bit depending on people's interest, really. There's so much that I can talk about, and so much that we do with our technology and our instruments for measuring air pollution and sensing the environment, and looking at all sorts of different gases in the atmosphere. And what I've decided to do, which I hope you're okay with, I've actually got two little presentations which I'm going to join. And one of them is about the advances in sort of laser-based technology that's being applied for environmental research, air quality monitoring, fugitive emissions monitoring. And the other part of the presentation is what I would call classic industrial emissions, air pollution from chimney stacks. And obviously, I used to come up here a lot when I used to go to various companies at Wilton, where we had the instrumentation measuring emissions from the various processes. So I'm going to talk about those two things, if that's okay with you. And I might run out of time, and if I do, then I think hopefully you'll find it all of interest. And I've also brought an instrument with me as well, and this is an example of a really high precision laser based instrument that's measuring methane and CO2 and water vapor. So this is a greenhouse gas analyzer that's used for lots of different applications. And after I finish speaking, I'd welcome anybody that wants to come and have a look inside this, because it's absolutely amazing how they've managed to miniaturize the technology that can measure these gases very precisely and very quickly. So without further ado then, so who am I? Well, I'm the MD of a company called Enviro Technology, and I've been with this business for 33 years. Despite my youthful good looks, so I've been there a long time. And I'm an environmental scientist, and my background really covers instrumentation, whether it's from servicing instruments, installing instruments, selling instruments, and even developing instruments. So I'm passionate about the technology and the instruments, and that's what's kept me in this job for pretty much all of my career. So that's a little bit about me. I'm very hands-on, so as I say, I'm the MD, but you'll generally find me playing around with new technology that we're looking to bring to market, or with a client demonstrating instruments. So I love the kit, and hopefully that passion will come through during my talk. So who's ET? Who's Enviro Technology? Well, we've been selling analyzers, instrumentation and systems for air pollution monitoring since 1983, so we're 40 years old. And after several years of incredibly good business, actually, even through the pandemic and outside, moving past the pandemic, our business has just grown and grown because of the interest in air pollution and greenhouse gas measurements. And we actually sold the business to a company called Curatere in December last year. So after 40 years of being independent, we are now part of a group that actually has 3 other environmental businesses. So that's just a little bit about who we are and what do we do. So the things that are in yellow highlight here are the things I'm going to talk to you about. There's other things that we do as well. Ambient air quality monitoring. That's our main business, and I'm going to touch a little bit about that. Continuous emissions monitoring. This is basically the emissions that are coming from chimney stacks and ducts from industrial processes and plants. I'm going to talk a little bit about the technology that we use to measure those, and I'm going to talk about greenhouse gas measurements because it's so topical at the moment. Other things I'm going to touch on are some of the instruments that we get involved with for measuring stable isotopes, remote sensing, atmospheric chemistry, and I will explain a lot of this terminology as we move through the presentation. I don't know what your backgrounds are from measurement and control, but I'm not, there's a lot of chemistry in here, so I don't know if there's any chemists in here. No, okay. So if you can see this poster from where you are, there's various things that we're involved with, and I could have talked about any one of these in any detail, so and I'm going to talk about some of them. So when we're air pollution measurement, you can make it in very many ways. You can make it from the ground, you can measure it from space, you can measure it from aircraft, you can measure it along fence lines, you can measure it at the roadside, you can measure it in moving vehicles. There's lots and lots of different ways that you can measure and sense the environment using technology, and this all helps us build up a picture of where the pollution is coming from, where it's going, what it's actually comprised of, and also how it's dispersing, how it's being formed, how it's dispersing. So we're best known for ambient air quality monitoring stations, and this is an example of a fixed ambient air quality monitoring station. So fairly big green hut, and inside that hut there will be a selection of different instruments that will be measuring various different gases in the atmosphere and particles. And gases such as nitrogen dioxide and ozone and sulfur dioxide, SO2, are all very bad for human health. They're also bad for ecology and for ecosystems, but NO2, ozone, SO2, they're all very reactive gases, and they are very well known for causing harm to people. And gases like benzene, toluene, xylene, these are the hydrocarbons, VOCs. Some of these gases are carcinogenic as well. So we have gases like SO2 and NO2 and ozone, which are really bad for our respiratory systems and our breathing. We have benzene, toluene, xylene. Some of those are carcinogenic, and then the particles that are in the air, what we refer to as PM10 and PM2.5. These are particles that are very, very small, 10 microns in diameter, and even smaller, 2.5 microns in diameter. These are generally all coming from combustion, particularly from vehicle emissions, and they actually get very, very deep into our lungs. They evade the body's inbuilt protection to sort of stop the larger particles that get stopped in our noses and our throats. But the smaller ones get deeper into our lungs, and the very, very fine ones get right through the alveoli and can get into the bloodstream, and they're very, very, very dangerous. So 50,000 people a year are dying in the UK prematurely because of poor air quality. And it's that cocktail of NO2, ozone, PM10, PM2.5. It's that cocktail of pollutants that's responsible. So our technology helps governments and the regulators to understand these concentrations and to make sure that they're kept at safe levels where possible. So these huts have got instruments in, and this is a picture of an enclosure, and inside there's some instruments in there. On the bottom shelf are instruments that measure NO2 and ozone, and on the top shelf we've got some instruments that are measuring particles. And we also have very small enclosures that just maybe measure oxides of nitrogen, NOx. So every town, every city in the UK, there will be these boxes that you'd spot. I always spot them wherever I go. I can always find air quality stations, but they usually blend in quite well to the sort of background, and they're usually bits of street furniture, so you'd probably be forgiven for not knowing what they are. But usually, they'll be at roadsides, curbsides, at very, very busy parts of towns and cities, and they've got instruments inside that are measuring the air quality. There's communications in those cabins, which is sending the data automatically to somebody that needs to get that data, and it's helping us build up a picture of how good or how bad the air is that we're all breathing. So the instruments that measure air quality tend to look like this. And what I will say, ambient monitoring, what I refer to as ambient monitoring, which is the air that you and I breathe when we're outside, that's ambient air, it's all around us. The concentrations of the gases that are harmful are actually very, very small, harmful nonetheless. So these instruments are measuring in parts per billion concentrations. So that's you know, 1 part per billion. That takes an awful lot of precision to be able to detect at that concentration. And these instruments are expensive. You know, an instrument that measures oxides of nitrogen might cost about 12 or 13,000 pounds, and that's just one NOx analyzer. But that is the cost of the technology to be able to measure down to these parts per billion levels with accuracy and precision, because we have to report the data to, we have to make sure that we are not breaching any limit values that are set by the government for these gases. So if you measure anything, you need to measure it well. That's always my philosophy, and especially when you are when there could be legal challenges if there's any ambiguity with the data. So the instruments are reference methods. They comply with CEN or ISO standards. So for NO2 and for ozone and for CO and for what have I missed out there? Ozone, SO2, CO, NOx. There are CEN ISO standards, and they detail specific reference method technologies that we have to use to measure air quality on our networks. So that's why the instruments are expensive. So a typical system might include a number of analyzers in a rack, like this picture shows you here. So in this rack, there might be an NO2 analyzer, an SO2 analyzer, a CO analyzer, an ozone analyzer, and maybe an analyzer measuring benzene, toluene, xylene, and PM10 and PM2.5. So that's giving us, you know, the full suite of air pollutants, the information from these instruments. And it's typically one analyzer per pollutant, because the measurement techniques differ considerably between one species and another. So a NOx analyzer will only generally measure NOx, it won't measure SO2. You need an SO2 analyzer, which will be using a different type of technology. So the more gases we need to measure, the more analyzers we need, and we put them together in a system. Okay, so one of the things I thought you might be interested to hear about is you know, what we've done with being able to put some of these instruments into vehicles, and to use instruments that are actually low powered, so we can make measurements whilst we're driving around. And there's lots and lots of applications where we do that, believe it or not. And we have a Nissan ENV200, which is it's like a Nissan Leaf. It's based on the Nissan Leaf, but it's a small van. So it's a zero emissions electric van, and inside that van we've put in a range of instruments that I use when I'm doing studies for clients. And the reason the van is zero emissions is because, well, obviously one of the biggest sources of air pollution that in our towns and cities is from vehicles. So when I'm measuring some of those pollutants, I don't want to be contributing to from my own vehicle. So the vehicle is 100% clean in terms of its no tailpipe emissions. And inside that vehicle, I've got a variety of instruments, and that, as you can see, the doors are open on this vehicle. There's an instrument that looks a little bit like this yellow one here, which is a greenhouse gas analyzer measuring CO2 and methane. And then there's some analyzers that are measuring NO2 and ozone and particles. And we also have a GPS positioning sensor on the roof of the vehicle as well. So whilst it's being driven around, we're also logging data of our positioning. So we can always then, when we take the data off the system, we can make maps showing pollution at different locations as we've been driving around. So it's quite powerful, and that's the real advance, because it's and again, because I'm a bit of a geek, I do like to talk about some of the tech that actually helps us with these mobile measurements. And believe it or not, I can get about 10 hours of power from two really small little lithium ion UPS battery packs. And these things weigh about 25 kilos each, so they're quite heavy. But with 2 of them, I can have 3 kilowatts of power, which will run all of the instruments in my van for about 10 hours continuous. And that's quite incredible, considering all these analyzers have got pumps in them, and but they're relatively low power. One thing a lot of people say to me, oh, well, can't you take the power from the van? If the van's electric, can't you tap into that to run your instruments? And the answer to that is no, unfortunately, because the battery systems in electric vehicles are, you can't tap into them to run anything else. They're all sealed. They're just taking care of the propulsion in the vehicle. You can't run anything else from them. So that's why I've got other power packs in there. And this just gives you an example of a plot of data that we did for the City of London in 2017, and this is about 5 days worth of combined data where we were driving around various streets in the square mile in the City of London, and we were able to then overlay the concentrations geospatially on a map, so we could really see where the hotspots were. So that's a really interesting sort of application for some of the more modern, faster, more precise monitoring technology. So we've sold into about 75 countries. We're not just in the UK, we sell our technology and we work all around the world. And we've even sold instruments down to the British Antarctic Survey's Halley base. And they have instruments where they're measuring, believe it or not, they are measuring the air down on the Antarctic peninsula there. And the reason being so is, even though it's so far away, we've created so much pollution and so much, since and the greenhouse gases. They want to be able to make measurements in these pristine locations just to be able to detect, what is in that clean environment. And there is pollution down there. It's you'd never believe it, but there is, including plastic pollution. And we even have instruments that are on board some of the UK's science institutes, like the National Environmental Research Council's FAM. This is an aircraft that is pretty much all the seats have been taken out and devoted to instrumentation, and they fly this around. They fly it over volcanoes, and they look at all the different gases from volcanoes, and they take it to other places to look at emissions from rainforests of methane and CO2 that's coming from the trees. So after 33 years, I'm still fascinated by the applications that people have for gas analyzers. It's incredible. So I'm going to talk about one particular technology that this instrument is based on. And this is a company that was started off in Silicon Valley in the San Francisco Bay Area in the USA, called Los Gatos Research, and a technology that they developed called off-axis ICOS. And I'll try not to bore you too much with what that is, but it's off-axis integrated cavity output spectroscopy. Bit of a mouthful. But it's basically a laser-based instrument that's measuring gases very precisely, very fast. And the instruments range in size from big sort of rack mount instruments to benchtop instruments to ultra-portable instruments like this one. But they're all based on the same laser-based technology. So greenhouse gas analyzers. There's been a huge push to better understand the concentrations of CO2 and methane, water vapor, N2O, nitrous oxide. These are the classic greenhouse gases. And not only do we want to be able to know what the concentrations are, I mean, I can tell you that in the room here now, there's 2 parts per million of methane. There's 486 parts per million of CO2. And that's good because it shows that the ventilation system is working quite nicely in here. The ambient CO2 concentrations outside are about 420 parts per million at the moment, and they're going up 5 or 6 parts per million every year, pretty much unabated. And they have been doing, as we all know, for since the Industrial Revolution. They've gone from 280 to the best part of 420 in 150 years, and there's no signs of them slowing down. But anyway, to understand that there's 490 parts per billion of CO2 in this room is actually quite good, because it shows that the ventilation system is working well. We're all breathing out, and if we were in a smaller room, you'd expect to see 1,000, 1,500 parts per million CO2. So CO2, methane and water, and 1 hertz to 10 hertz, and that's important, because some of the applications that these instruments are used for, they're looking at very, very fast responses or fluxes, 1 hertz to 10 hertz. So 10 hertz is 10 measurements per second. That's very, very fast, and you need super precise, super fast laser instruments to be able to do that. So 10 measurements per second. Isotopic analyzers, so nitrous oxide, CO2, methane and water. There are different isotopes of nitrogen and carbon and hydrogen, and we have a need to be able to understand what the ratios of those isotopes are for some applications, and we use off-axis ICOS to be able to do that for us. And then trace gases, like ammonia, NO2, hydrogen sulfide, hydrogen fluoride, hydrogen chloride. These are actually all very tricky gases to measure with older technology because of their reactivity, and their hydrogen fluoride is very aggressive, so is hydrogen chloride. Ammonia is very, very sticky, so if you try to measure ammonia with an older type of technology, you'll find that it will stick to the surfaces of your tubes, and you might end up measuring a lot less of what actually went in the tube in the first place. So measuring it with a laser very quickly, we can overcome a lot of these problems. And other gases in combinations like methane and acetylene and ethane. Okay, I'm not going to go through that. That's a little bit boring, but the technology is based on something called Beer-Lambert law, and Beer-Lambert law is quite a classical old law, and basically it's telling us that the concentration of a substance can be determined if you understand the absorbance, the molecular coefficient, the molar concentration, and more crucially the length of the path. So if you know what all of these factors are, you can actually arrive at a concentration for a particular substance. So Beer-Lambert's law is what we use, and we're measuring in the visible part of the electromagnetic spectrum, which is represented on this graph here. So you can see the lovely spectrum of colour there. That is the obviously the visible part of the spectrum, but we're actually measuring right in the infrared, the infrared and the near infrared part of that spectrum with this kind of technology. And you can see some of the gases that we can measure depending on whether we're in the near infrared or the mid infrared. And depending on the type of laser that we have in our instruments, we can actually determine different gases. So the common laser, which is a diode laser, which is in this instrument, these used to be extremely expensive, and they've become cheaper and cheaper and cheaper over the years. So, you know, a diode laser in an instrument 10 years ago might have cost £20,000. Now maybe £1,000 for the same kind of laser. So that's why lasers are becoming so they're in the world of gas and particle measurement. It's all about lasers at the moment. There's a big movement to measure these things with lasers because you get the precision and the speed. So we can do things like CO2, methane, ammonia, NO, hydrogen sulfide with a diode laser. And then we can also measure things like N2O with a quantum cascade laser, which is a different type of laser, which is still very expensive. A QCL laser in an instrument might be £10,000 just for the laser. So to measure some of these species can get quite expensive. And really, just to explain how it works, the off-axis ICOS is we have a laser beam which is pointing into a cavity, and the cavity will be a different length depending on the instrument. But the cavity in this instrument, when I show it you, is probably about this kind of long, so whatever that is, 10 inches or something like that. So short cavity in this instrument. And there's longer cavities depending on some of the benchtop instruments. But basically, although it's a short cavity, the effective path length is several kilometres, because we are shining a laser into this cavity, and there are a pair of highly reflective mirrors either side of the cavity, and the laser energy is bouncing off those mirrors tens of thousands of times, so it's effectively a very, very long path length. And then eventually some of that energy will come out of the other end of the cavity and is focused onto a detector. So some of those photons will come out and hit a detector, and the instrument can then make measurements once it's got that energy from the cavity. And the gas is being, you can hear a pump in this instrument. So we're sucking air into the cavity, and the air is coming back out of the cavity, and all the while the laser is shining into the cavity and making this multi-pass path length, which is several kilometres long. And that's what we need to be able to measure. We're measuring parts per million with these gases, but we're measuring them with parts per billion precision. And for that precision, you need a very long path length. And that is all part of the Beer-Lambert law. So short path, usually higher concentration, longer path, lower concentrations can be resolved. I'm not going to go through that because that's a bit boring, and just really talk a little bit about the applications. This ultra portable instrument that we've got here is generally used by researchers in universities who are looking at the actual very small fluxes of CO2 and methane in the atmosphere, how different types of soils and vegetations can act as a sink for these greenhouse gases, and how they can take them in. But there's fluxes going on, so there will be a natural take-up of CO2 by the vegetation and the soil. But some of it will come back to the atmosphere because it's always in equilibrium. Something's coming in, something's coming back out. And the researchers will normally use these instruments with a chamber. So they'll put a like a plastic chamber over the soil, and they'll have the inlet going into the chamber and the outlet coming back, and it's a closed loop. And periodically the chamber will open, so that will expose the vegetation to the atmosphere. Then the chamber will close, and then the instrument will be measuring, and there'll be some fluxes going on within that chamber. And they need the precision to be able to do those measurements. So the ultra portables are used for that. This instrument can also be used with a shoulder strap and a telescopic wand, and that's when it's used for leak detection, because it's measuring methane here, and it's measuring it very, very precisely. One of the big applications that's not really happening here in the UK, but it's happening in America and elsewhere in Europe is where people are getting very, very serious about trying to quantify methane leaks from industry. So they will have people taking these to site and going around pipelines, and they'll be sniffing sort of valves and joints, and they'll be looking to see whether there's any methane escaping. Because it's going into the atmosphere, and methane is, I can't remember, 50 times more damaging than CO2 from a global warming potential. And also, if there's any methane coming, being leaked from a process, then the process is losing money. Yeah. You know, methane is natural gas. It's well, you know all about energy prices. So that's one application for it. Is where it's being used as a leak detection system for sniffing out methane leaks. And there's also a lot of applications for it from an environmental research perspective. So this is the instrument I've got here, the micro portable. So this is only 5.5 kilos with an internal battery. So it's not plugged into the mains or anything now, it's just working on a battery. So for people doing this kind of research in the field, 10 years ago, they would have had to have taken a sample into a canister, and they would have had to have then sent that canister back to a laboratory, and they would have had to have used a much bigger, much heavier, much more expensive instrument in the lab to measure what's in that canister, because you just couldn't get the instrumentation small enough or light enough or low power enough to bring it into the field. But now you can. So this has really revolutionized a lot of research. People are using it in Antarctica, people are using it in the Amazon, people are using it in all sorts of applications where they want to make these accurate greenhouse gas measurements. And it would never have been possible 10 years ago because A, the lasers were prohibitively expensive, the instruments were too heavy, so now things are getting smaller. So moving on, this is where it gets really exciting now. So believe it or not, the actual bench, the little cavity in there with the lasers, it can actually be made smaller now, small enough that it can actually fly underneath a drone. And this is actually quite a big drone. This isn't your normal kind of hobbyist drone. This is a far more sophisticated drone, larger drone. And this will actually fly one of these greenhouse gas analyzers for, I don't know, up to half an hour. It depends on how much, because it weighs about 2 kilos. So that's quite a lot of weight for a drone. So, they're limited to the amount of battery power that can keep the things in the air. So maybe half an hour one of these can fly for. And they typically have the greenhouse gas analyzer, but then they'll have a GPS sensor, so they know their positioning. There will also be a anemometer, so as it's looking at the wind speed and the wind direction directly above the rotors, and it will be sending that information back to a tablet or a computer. So what I want to just show you now really is some applications where people are doing this. So pictures on this graph here, you might see there's a field of cows, and there's one of these big quadcopter drones with a greenhouse gas analyzer. That was actually, I believe, in Manchester, where we were doing some pilot studies with the University of Manchester with this technology. Obviously, agriculture is a big source of methane emissions. Probably the biggest source of methane emissions after natural gas is from agriculture. So quantifying the methane emissions from large, herds of cattle, particularly in the US, where they can have, thousands and thousands of cattle on some of these ranches. But more typically, it will be for industrial applications where these will be flown over gas processing plants or refineries, and they will be looking for leaks specifically from the air, which is a lot more efficient than having somebody walk around with one of these on a shoulder strap and a wand trying to sniff every single pipe. So if the drone can actually find where the leaks are, then somebody can come out and sort of verify that with an instrument, and then they can do whatever they need to do to fix that. So this gives you an idea of how the drone-based monitoring can help people. And the drone was actually programmed to fly an automatic flight path, which is shown on the right-hand side of the graph there. So as you can see, it was flying these kind of zigzags on a pre-programmed route at 40 meters, and it was flying at 15 miles per hour. So 40 meters altitude, 15 miles an hour, and it was flying around this pre-programmed route. And the graph on the right is predominantly blue, but you will see that there are some green, there are some little green parts that are towards the bottom half of the chart, and basically that's where the methane concentrations are starting to increase. And I haven't got a laser pointer to show you, but there's on the left-hand side of the graph of the chart, there's 4 graphs, and the one at the top is showing the methane concentrations. So they're able to, as they're flying the drone around, they're seeing the methane concentrations changing, and they're able then to pinpoint where those leaks are. And this is another example, and this time the drone is being flown around manually, so it's not following a pre-programmed flight path. The operator is just flying it around, and again we can see different colours on that wiggly squiggly chart, but they are corresponding to different concentrations of methane that the instrument is picking up whilst it's being flown around. So that's a really interesting application of this type of technology. The instruments can actually be much bigger than this, and the bigger ones tend to have more temperature control. So these ones, the temperature of the cavities are kept at very high tolerances, millikelvin precision. So the temperature of the cavity is kept very constant, very critically, and that enables them to be even more precise. And this is an example of a university super site. This one's at Manchester, and there's a rack in there, and on the left hand side of the rack are some of the instruments that I talked about earlier that are measuring things like NO2 and CO and ozone, and on the right hand side are some of these Los Gatos research analysers that are measuring methane, CO2, ammonia and water vapour. Just to tell you another little application now, so benchtop instruments, we tend to sell these for liquid water isotopic measurements, and that does sound a bit of a mouthful, and essentially what we do, or what our clients do, is they're interested in the different isotopes of oxygen and hydrogen in water samples, actually. So whether we're looking at I've got to remember this now. So carbon 13, carbon 12 is the main isotope of carbon. Carbon 13 is another isotope of carbon, but it's very small concentrations of it. And the same with water, so H2O. H2 is deuterium, and oxygen, normal oxygen is 16, but there's also oxygen 17 and oxygen 18, and these isotopes are present in much lower concentrations, but they're present. And what they tend to do is they tend to help researchers and hydrogeologists understand where the source of water came from as it travels underground and through aquifers and in various parts of the world. So oceanic water has a different isotopic signature to fresh water. Glacial water has a different isotopic signature. So we have an instrument that's actually sampling from little vials of water that the researchers have bought from wherever they've been making their sampling. And we put it into an instrument that automatically then takes an injection from each of these little vials, vaporizes it into water vapor, and then measures it with this off-axis ICOS technology. And we're able to look at the ratios of the different oxygen and hydrogen isotopes. Now, one application for this is really interesting, and it comes to do with sort of counterfeit products. Olive oil, Scotch whisky are two examples. So, counterfeit Scotch whisky. Obviously, there are some very sophisticated, like with all things, there's some very sophisticated fakes these days, and it comes down to things like olive oil can be not from Italy or from Spain, and Scotch whisky may not originated from Scotland or the Isle of Mull or wherever. It might be from China. That's just an example. I've got nothing against China. However, by analysing the isotopic signature of the water that's in these products, whether it's olive oil or whisky, we are able to understand where the water came from. So if something is being branded as Scotch whisky and sold at a premium, but it's actually it's counterfeit, it's being made in Europe, or it's being made in China, or made in India, but with a Scotch whisky label on it, we can tell where the water came from, because it will have a different isotopic signature, because the ratio of hydrogen and oxygen in the water will be different. And this technology enables people to do things like that. That's a small application for it. The big application is understanding how water moves underground, and where it actually originated from, and whether it's fresh water or glacial water. And then really the microportable analyzer is the one that I've got here. And again, since this has been made small enough, it's been taken everywhere where people want to do research. And this picture is in the Arctic as opposed to the Antarctic. And this is up in Alaska at 70 degrees north, where a researcher is using one of those chambers over the ground, and the instrument is running off a battery pack. And this just wouldn't have been possible 10, 15 years ago. They would have had to have gone out to Prudhoe Bay in this instance, filled a canister with gas, and they would have had to have flown it back to the laboratory to make the very same measurements that instrument is measuring in situ. And another example here, this is out in Borneo, where they're looking at the fluxes of carbon and methane from the atmosphere into the soils and the vegetations. And one of these instruments was recently used in a paper where that was ultimately published in Nature, and it was probably one of the most prestigious papers in the field of gas flux measurements from the atmosphere to vegetation. And it was a team of people who went to the Amazon, and they were using one of these in a boat, and somebody was sort of rowing the boat on the tributaries of the Amazon, and they were actually taping chambers onto the sides of trees, and they were looking at the methane and the CO2 coming off the trunks of trees using one of these instruments to make those measurements. It enabled them to be able to prove that the majority of the methane from trees is actually coming from the trunks and not the canopy, which was first thought. So, and that was actually published in Nature. So that was probably one of the sort of highlights of that kind of research. And that really, I think, is it from me. I have another presentation, but I don't know whether you wanted to have a look at this instrument, and if you want me to tell you a little bit about our SEMS stack emissions monitoring, I'd be happy to do so. Okay, so I'll run a few more slides here, because I think it might be interesting for you. And this is another type of technology. So I talked about that, which was off-axis ICOS. And I'm going to talk about some technology called DOAS now, which is differential optical absorption spectroscopy. The thing that's common between that and this is the spectroscopy bit. And basically, DOAS is a technology that uses light as an energy source, and it looks at the absorption of different molecules within a path. And that path can be a short path, which could be across a stack or a duct in an industrial context, or it could be over a very long path, which might be 500 meters or even a kilometer or so in the open atmosphere. Doesn't make any difference. The technology can measure those molecules in a long path, and then on that example where I said 500 meters or a kilometer, you'll be looking at parts per billion. But in a short path across a stack, because the concentrations will be contained in a smaller area, the concentrations will be higher, and they will normally be in parts per million. So it's the same technology, but the path length will change. Now, the advantages of this kind of technology over some of the other technology that I showed you, when I told you about individual analyzers, normally one analyzer measures NOx, one measures SO2, one measures ozone. With these DOAS type analyzers, we can resolve different gases simultaneously in one analyzer, because it's using spectroscopy to resolve those wavelengths. And the example I mentioned, the open path example, where we have an emitter and a receiver, this can be 500 meters, a kilometer, or even longer in the atmosphere. And we use an emitter, a receiver, and an analyzer, and we use fiber optic cables. So it's very simple in its concept: an emitter, a receiver, an analyzer, and the fiber optic cable. And I will explain that. And how that open path system looks in practice is like this. And the picture on the left is showing you this is actually a transmitter, and you can see a ship, and that transmitter is firing a broadband energy source across an open path across the mouth of a harbour. And as the ferry boats come in and out of the harbour, the SO2 emissions from the diesel engines is being measured, or the bunker fuel engines. So using this transmitter and a receiver and having an open path through the atmosphere, we're able to then line that up over a particular area of interest. In this case, it's a port. They're interested in seeing the contribution of air pollution from those exhaust stacks on the ships. Because the ships are coming into port, it's a town, a city, people live there, and there's a pollution enough as it is at the city, and the ships coming in and out are contributing even more to that sort of pollution. So understanding that is interesting. And the example on the right is actually in Swansea, here in the UK. The picture on the left, actually, with the port is in Sweden, in a place called Helsingborg in Sweden. Picture on the right is in Swansea, and they're measuring along the side of a busy arterial road that's bringing a lot of traffic into the city of Swansea every day. So they're measuring different types of pollution over that light path. But you can see how this emitter, receiver, analyzer concept is working. And the picture I showed you earlier of the chap in the enclosure with all these different analyzers for NOx and SO2 and CO and ozone, all of that could be replaced by just one, in this case, blue box, which is a DOAS spectrometer. And then for stack monitoring, which is the other application, instead of that big long light path through the atmosphere, we're using a much shorter path across a chimney stack. And we're using the same kind of technology, an emitter, a receiver, and either one or two types of analyzers to collect that light and make the measurements. But it's what we call cross-duct. So it's a cross-duct non-contact measurement. We're not extracting the gas with a pump like this instrument is. We're measuring the absorption of the gases as they go through the stack. And that has a lot of advantages. You're not handling the gas. You're not trying to extract it. And when you extract a gas out of a stack, you run the risk of not necessarily sampling exactly what went into the probe at the start of the process. You can lose a lot of that stack gas on its way back down to the analyzers. So it's not doesn't tend to typically be as precise or accurate as measuring across the stack if you can do so without touching the gases. Okay. We had a big system up here actually at the GDF Suez plant when it was operating, the big gas turbine power station in Teesside. So we had I think that was 9 or 10 gas turbines, but each one of them had one of these cross-duct analyzers measuring the emissions going to the atmosphere. So that's an example of a SEM system up in this part of the world in Teesside. And we put that system in, and it ran for about 18 months, and then they shut the plant. So you'll probably all know about that. That was at least they paid for the kit from us before the plant shut. But it was a bit of a waste, I think. But it was a classic example of how you can use this cross-duct technology to measure the emissions from each of those gas turbines. And gas, obviously, is a lot cleaner to burn than some of the other processes like coal. However, there is quite a bit of pollution that comes off those gas turbines, particularly NOx, oxides and nitrogen. Okay, so I'm going to show you a bit more. So this is an example of what's going on in the stack. So we have an emitter and a receiver, and we have some molecules there in the stack. SO2, I can't read that from here. SO2, ammonia, NO. So the light goes across the stack. The light is interacting with these molecules, and then we have some measurements that we make with a spectrometer. And we use, inside the transmitter, we use a xenon lamp. And the xenon lamp is chosen for the sort of broad band of wavelengths that it generates, because some of these gases that we're measuring are absorbing in the ultraviolet, some of them are measuring in the infrared. But the xenon lamp is broadband. It's visible. When one of these lamps is on, it's like a car headlight. You can see it. But what you can't see is the UV at one end of that spectrum or the infrared at the other end of the spectrum. So we use a xenon lamp which shines across the stack, and we use some fibre optic cable which collects the light from the receiver, which the transmitter is focused on, and that fibre optic cable introduces the light into a spectrometer. And the analyzer looks like there used to be a black box in the old days, but now they paint them yellow. But it's, there's no display on there. It really is just a quite a big, heavy instrument. But this is the spectrometer. This is the bit that works its magic to be able to resolve and tell us what those concentrations are. And how it works. Again, I wish I had my laser pointer, but I don't. So on the left-hand side, we have the light source, which is that xenon lamp, which is firing across the stack. We have a whole range of different molecules of different gases that are going through the stack. SO2, NO, NO2, water, hydrogen chloride, mercury. The light then hits a mirror in the back of a receiver, and it focuses the light down a fibre optic cable. And basically the light is then projected onto one mirror. It's projected back to something we call a grating. The position of the grating then sends the light back to another mirror, and then eventually the light comes out of the back of the spectrometer and hits a detector. And the grating is the important part of this, because the grating is what is breaking up that white light, that visible light that's shining across the stack. The position of the grating dictates which part of the spectrum the detector is focusing on. And as we all know, these molecules are absorbing in different parts of that electromagnetic spectrum. So the grating is the key thing to being able to resolve different species. And the grating is an optical device used to separate light with different wavelengths, and it's got something like 100 or up to between 100 and 1,000 scores per square millimetre on this glass surface. So it's a very, very precise piece of glassware with these microscopic scores, which, depending on the position of the grating, depends on which part of the spectrum is then being focused on for analysis. So yes, 300, 600, 1200 or 3600 lines per millimetre, so high precision. And it's controlled, the position of it is controlled by a stepper motor. So the stepper motor is turning that grating a few degrees to be able to look at different parts of the spectrum. And then, like a little bit like the greenhouse gas analyzer, some of that energy then hits a detector. In this case, it's what we call a photomultiplier tube, and that photomultiplier tube is amplifying the signal of and converts it from analog to digital, where we then make measurements. And there's a sweep wheel that's spinning round, which is actually modulating that light. So we're building up a scan of that light that before it falls on the detector. So it's a pulsed modulated signal which hits the detector. Okay, and So what does the hardware look like that goes onto the stack? Well, we have a couple of lumps of hardware. We have the the picture on the left-hand side is the receiver. That's a stainless steel box, and there's a mirror in there, which the fibre optic cable connects to. And on the right-hand side is the transmitter, so that bolts onto the stack, and that contains the xenon lamp. So that's the hardware. And what we have to do is we have to introduce some purged air before the receiver and after the transmitter. So the purged air is just protecting the optics, because some of these processes where we're measuring the air pollution from stacks is dirty. There might be lots of particles, and if you didn't have some purged air, which is just instrument air, just keeping a little positive pressure on the optics, the optics would plug up with dust, and none of that energy would then be able to get across the stack. So it's self-cleaning essentially. So we're keeping the optics clear by using that purged air. And this is how a system looks in practice. So we have the emitter and the receiver. We have maybe one or two analyzers, because this time we have one analyzer measuring gases that are UV, which are like NO, NO2 and SO2. And we have another analyzer which is measuring the infrared absorbers like CO, CO2, HCl. So one or two analyzers. And then we also have to measure things like pressure, temperature, dust, flow, oxygen, because for a lot of these processes we need to be able to normalize them to temperatures and to known to process temperatures and pressures and whatever the oxygen concentration is. So we have to have other things than just the instruments that are measuring the gases. And because it's an optical system, we can actually switch. We can have several sets of emitters and receivers, all connected to just one set of analyzers. And instead of using pneumatics and lines, we're just using these fibre optic cables. So we can actually have 1, 2, 3, 4, 5 light paths connected to what we call a multiplexer, and the multiplexer then is switching whether it's stack A, stack B, stack C, stack D. So we can measure multiple stacks with just one set of analyzers, and we just switch the fibre optic cable automatically. And that's what the multiplexer looks like. We have 1, 2, 3, 4, 5, 6, up to 6 fibre optic cables can go into it, and then one cable comes out to the analyzers. So again, it's we're using spectroscopy. We're not using lasers in this case. We're just using a xenon lamp, but we're using fibre optic cables to collect the energy. And there's no contact with the gas. We're not actually extracting any gas or doing any sampling. So it's all cross-duct, non-contact. I'll just finish up with this now, because I think I probably have gone on for too long now. But what do we use it for? So we use it for all manner of industry. Aluminium smelters, and I've mentioned to a few people that I used to come up to Teesside quite a lot and go a little bit further north, because we used to have this technology at the Alcan smelter at Ashington. And do you know what they did? They had the open pat. It wasn't the stacks that we were doing with that system. It was the actual pot rooms. So there was an emitter and a receiver in the roof space above the pots. So that I can't remember how big those sheds were. They were 500-600 meters at least. And the reason it was there, it was measuring HF, hydrogen fluoride, which is obviously. Hydrogen fluoride is a very, very nasty gas. It's very bad for you if you breathe it in sort of high concentrations. So, the pot room operation there, the ingots are put into the pots, and the cathodes are applied, and they put through this huge current, which is then melting the ingots. But periodically they have to open up the pots and they have to change the ingots, and then people are in there working, and hydrogen fluoride is extremely dangerous. So they're measuring the hydrogen fluoride in the pot rooms from a health perspective of the workers, but also that HF has to be collected and that's when it goes up the stack as well. So that's what we were doing there at Ashington. But brickworks, cement works, chemical, fertiliser, glass, you name it, power plants, refineries, whenever there's a stack, whenever there's a process, we can measure some of the pollution that's going through those stacks with the technology I've just described. And I'm just going to finish up with an example of some of the ranges that might be of interest, because we have to have what we call MCERT certification these days. So the Environment Agency, about 20 years ago, the Environment Agency really started to tighten up the regulations and the processes they couldn't just go and buy the cheapest bit of kit to measure emissions. They had to go and buy and fit quality assured kit that was type approved and reference method. So the data that was being reported to the Environment Agency could be relied upon, because they were using the right technology that's got the right approvals and could get to the low levels that they needed to. So MCERTs is a scheme that came in and basically to sell instruments into some of those processes.